How has PID controller design evolved to remain so relevant? Imagine trying to keep a boat steady on choppy waters or maintain the temperature in a room perfectly balanced. That's what a PID controller does in many electrical systems. It's a simple idea that has stood the test of time. Originally created in the early 1900s for steering ships automatically, it quickly proved useful in many other areas. Today, it's still one of the most common tools in control systems because it works well and is easy to understand. A PID controller adjusts a control variable based on three parts. The proportional part reacts to the current error, which is the difference between what you want and what you have. The integral part looks at the sum of past errors to fix any steady mistakes. The derivative part predicts future errors by considering how fast the error is changing. Combining these three makes the system stable and accurate. This simple setup is used to control voltage, motor speed, temperature, and more in electrical engineering. Over time, engineers have made many improvements to keep PID controllers useful. They often use simpler versions like PI, or PID controllers when full PID control isn't needed. For example, a P controller might be enough to control a motor's speed if a small steady error is okay. A PI controller is better when you want to eliminate that steady error completely. These options let engineers choose what works best for each system, saving costs and complexity. Tuning a PID controller used to be a slow process, done by trial and error. Now, software and algorithms like Ziegler-Nichols or Cohen-Coon help find the best settings faster and more precisely. This means systems respond quicker, overshoot less, and stay stable. For complex systems, Cascade control uses two or more PID controllers working together. The outer loop manages the main process, while the inner loop handles faster changing parts. This setup improves response and stability for systems with multiple variables. The shift from analog to digital control has also made a big difference. Digital controllers run on microcontrollers and programmable logic controllers. They can change parameters on the fly, connect easily with sensors and actuators, and handle complex calculations. This makes PID controllers adaptable for modern applications like robotics, power electronics, and automation. Recently, combining PID control with smart algorithms like fuzzy logic or neural networks has made controllers better at handling nonlinearities and uncertainties. These hybrid systems keep the core idea of PID but add the ability to adapt to changing conditions and tricky environments. In electrical engineering, PID controllers keep variables like voltage, current, motor speed, and temperature in check. They process signals from sensors and adjust outputs to keep systems running smoothly. For example, in motor control, they use encoder signals to maintain precise speed or position. In power systems, they help keep voltage levels stable and frequency steady. Their ability to be tuned and adapted makes them a reliable choice, even as technology advances. All these improvements show why PID controllers are still so important. Their simple design, combined with ongoing innovations in tuning and digital implementation, keeps them relevant. They can handle everything from basic feedback loops to complex, multivariable systems, making them a staple in electrical control systems today.